Yes, class, am I audible to all of you? Humam, Austin, Faiza. Faiza, you were absent yesterday? Yes, class, am I audible? Okay. Fia, what about you? Both the classes you have missed. You were so eager about all the classes regarding your exams also. Now when the classes are going on, you're missing on it. After class assessment also, you're not attempting Fia. In both the batches, the syllabus is moving on. Humam, Madiha, Tarif, and Shahid. Okay. C class. Let us complete this lesson, Earth magnetism. Okay, Fia, no worries. We have Gauss theorem we have studied in the last class. Not in the last class, in your electrostatics, we have studied Gauss theorem. So what was Gauss law? E dot ds is equal to q over epsilon naught, right? Closed integral of electric field is actually equal to 1 by epsilon naught times the charge that is enclosed. This is Gauss law in electrostatics. This is Gauss law in electrostatics. Now, a magnetic field is produced only by a magnetic dipole because we know isolated poles cannot exist. Yesterday we had seen a property, no, magnetic monopoles do not exist. But when we talked about electrostatics, we could see that due to only a single charge, we can obtain electric flux, right? Electric flux can be obtained from it. But when we talk about magnetism, in magnetism, this is not necessary, right? Because isolated magnetic poles do not exist. So if magnetic poles do not exist, so surface integral of magnetic field over a closed surface, that is B dot ds, this becomes 0. Because here isolated, this is valid for isolated charge and this is not valid for isolated charge. So Gauss's law in magnetism states that surface integral, this is what? This is surface integral. Surface integral of magnetic field over a closed surface is 0. But the surface integral of a magnetic field over a surface gives what? Magnetic flux through that surface. You get magnetic flux. This formula is valid. But at the end, you have it as 0. This is what is known as Gauss law in magnetism. This statement, Gauss law in magnetism. This is what is meant by it. So you can compare it always with the electrostatic part as well. All right. Now see, what are the consequences of it? Because magnetic monopoles will not exist. Magnetic monopoles won't exist. See, this is what is written. Magnetic field is produced only by a magnetic dipole because magnetic monopoles do not exist. Now, apart from all these, Gauss law in magnetism states that surface integral of magnetic field is 0. This is what we have studied. Now, what I wanted to tell you apart from this is that certain consequences of Gauss law you should know. See, one thing that you should remember is that Gauss law, this indicates that there are no sources or sinks. Sources means from where the magnetic field is being generated. Sink mean to which the magnetic field is getting enclosed inside a closed surface. So there are no starting, there are no endings. Basically, what does this mean? That isolated magnetic poles, which means monopoles do not exist. Isolated magnetic poles, which we call as the monopoles. They do not exist. Second point which you should remember is that magnetic poles always exist as unlike pairs. Magnetic poles magnetic poles always exist as unlike pairs. Unlike pairs means of equal strength. Strength is same, but polarities are opposite. Okay, and see, now if one more thing that you have to remember in here. Yes, Chavez. No, nobody has written anything till now. I'll give you from the starting. So just listen right now. Notes have not been missed by you. You'll be able to write them. And last thing, if see a number of magnetic field lines are entering a surface. Suppose this is a surface. This is entering. So this will only leave. If this is entering, this is leaving. This is entering, this is leaving here. This is entering, this is leaving. So number of field lines that are entering 1, 2, 3, 4 is equal to number of field lines leaving 1, 2, 3, 4. So basically they never terminate, right? These are magnetic field lines. This is a closed surface. So number of field lines entering is equal to number of field lines leaving. This is it. That means if a question comes for consequences of Gauss theorem, this you can write. Because in one question paper, I had seen this, just one question paper. This is not a very repeated question that comes. That's why I just made you write these 3 points separately. All right. You people have not performed well in the test which we had, where we had talked about Ampere's circuital law that was given, where you had to prove that the electric field on the axis of circle. Remember this question paper that we had? Who all have attempted from here? Tarif, Humam, Faiza and Austin. I think these many only have attempted. Chavez, you have attempted. Let me just cross check because you people have not performed well in that. Only Austin has done fine. Shahid was saying, oh, Chavez, you have given. Humam 9, yes, Austin 17, Tarif 6, Faiza 11. Chavez paper I haven't received. Did you understand the paper I was talking? Ampere's circuital law was the first question. This paper, Chavez. Fine, let me then just ask them for the paper. Because Chavez I didn't receive. So you people have not done very well in that.
It was related to magnetic field, right?
Let me ask for your paper. Anyways, so Gauss law in magnetism is this. So whenever Gauss theorem comes, you have to be careful. So what is the final conclusion from this? Closed integral of magnetic field over a closed surface is 0. This is your magnetic flux. Though we'll start with magnetic flux only EMI, there we'll discuss how to calculate magnetic flux and everything in detail. After Earth magnetism, we'll start with EMI, where we'll do magnetic flux as the first topic. Right now, note it down. Let's then begin with Earth magnetism. Okay, Shaviz, I'm cross-checking. Just give me a minute. Now class, we have to do, this one topic is left from this lesson, Earth's magnetism. Yesterday, did you all have a look at that table? Your after class assessment was also based on this. Now see, first we'll understand certain terms which have relation with Earth magnetism. Some definitions in connection with Earth's magnetism. So with the help of a figure only, let us understand this. That will be easier to understand which axis, which terms. See, suppose this is Earth. All right. Now we are assuming Earth to be a magnet. We are assuming the Earth to be a magnet. Fine. Now, what all things are present if this is a magnetic? Remember, I have told you certain definitions of magnet. Magnetic axis, we discussed. What was magnetic axis? Magnetic axis is a line that is joining the North Pole and the South Pole. Oh, this is a lot tilted. The Earth's axis is not this much tilted whenever we draw it. I do not know what is the exact angle of tilt. Anyone who has any idea what is this angle that the axis of the Earth makes with the vertical axis? Please let me know if anyone knows this. Okay, secondly, now Earth's magnetic field lines are flowing. So there are two axes present. 90 degree? No, Fia, 90 degree, how can the Earth's axis be at 90 degree? From the equator, are you saying? From the equator, it can be 90. From the vertical, I'm asking. It's not 90 from the vertical. Just check if anyone knows from Google or somewhere. I do not know this. Okay, so yes, I was telling you, there are two lines that have to be drawn. See, once I have told you that there are magnetic axis lines. So this we call as the poles line. Suppose this is your south polarity over here. This is your north polarity over here. And this is the north pole. This is the south pole. So this line, this I am referring to as, this is Earth's magnetic south pole. From where now the lines will be entering. This is Earth's magnetic south pole. Fine. This is magnetic axis. This green one which I have drawn, this is magnetic axis. Similarly, here we have magnetic north pole. Got it? This one, all these lines which are coming out, these are magnetic north pole. Magnetic north pole. Now remember class, one more line I have told you, the line that is perpendicular to the magnetic axis, 23.5 degree. Okay, Faiza, thank you so much. 23.5 degree is that angle. Okay. Anyone who remembers, we did that a line that crosses, that connects north and south pole is magnetic axis. What do we call the line perpendicular to it? Yes. Alia, line perpendicular to magnetic axis. Chavez, can you answer?
Magnetic equator.
Magnetic equator, very good. We studied magnetic equator and there is already an equator of Earth. So this equator is actually your magnetic equator. That's why we discussed all these terms. This is magnetic equator. So this is all regarding magnetism, right? Now, one axis which Faiza has searched for us, that is the actual angle of axis of rotation that is present. There is one axis of rotation, no? And in the axis Earth rotates. Let me draw it straight, then it would be clear. Wait. See, this axis on which the earth rotates, earth does not rotate on its magnetic axis. We all know earth has its own axis for rotation. This is magnetic axis is different. So magnetic axis is different. This is the axis if earth behaves as a magnet, right? This is geographical axis of rotation. This angle Faiza has found for us. Faiza says it's 23.5. So this is geographic axis of rotation. This is geographic axis of rotation. On this axis, the earth rotates. Now, magnetic field lines are actually what? If they are coming from north, they'll terminate in the south. Like this, if they are coming from north, they will terminate in the south. And within, they will move from north to south. Then again, they will move like this. This is the entire, and like this, entire earth has been divided. Fine. So what all things you have to remember here? Firstly, you have to know the geographic axis. What is a geographic axis? It's a straight line that is passing through geographical, let me write it, straight line passing through geographic north and south pole. That geographic north and south pole, this means the actual north pole we say, towards north, situated towards south, east, west, that north pole. And when we say magnetic north pole, this is the magnetic polarity if earth behaves as a magnet. So this is through geographic north and south poles. So this is one term. Second, magnetic axis. Magnetic axis definition you people have already written. Magnetic axis is what? This is an axis. This is a straight line passing through the magnetic north and magnetic south poles of Earth. Fine. This you should remember. Second, you have magnetic equator. Third, sorry, not second. Magnetic equator. This is also perpendicular to it. This is also what we have discussed. Now you have magnetic meridian also. The way we have no geographical meridian. One, you have a geographical meridian. One is a geographical meridian. Now, what's a geographical meridian? It's a vertical line passing through the geometrical North Pole and South Pole. This is the line which I was asking you. From geographic meridian, I was asking the angle of inclination, which Faiza told that is 23.5. So geographic meridian is this straight vertical line that is passing through North Pole and South Pole. Obviously not this straight, this is wherever the North and South poles are located. And when we talk about the magnetic North and South pole, these are the geometrical North and South pole. If we talk about the magnetic, then that becomes magnetic meridian. Vertical line that is passing through magnetic axis only, because magnetic axis also does the same work, but it can be different. Earth's magnetic field acts in the direction of Earth magnetism. This you should remember. Earth's magnetic field acts in the direction of magnetic field. This is magnetic meridian. So these terms you should remember. Now we'll come to angles and we have certain formula through this. But first you should note down this, otherwise it will be confusing. Some terms in connection with Earth's magnetism. Class, now a little bit of calculations. The angles which I wanted to mention to you. See, there are certain angles which you have to remember, but with respect to both the medians, geographical median is there and you have magnetic meridian. Suppose this is the geographical meridian. This one is geographical meridian. Then we have a magnetic meridian. This will be a magnetic meridian. Now suppose this is the magnetic field of Earth. This is the magnetic field. This is the total magnetic field. So the angle that the magnetic field makes with the magnetic meridian, this we call it as gamma, delta. That is the angle of dip. This is angle of
The magnetic meridian means
this is the
magnetic axis,
angle
right?
that the magnetic field makes with the magnetic meridian, angle of dip. Fine. Now there is one more angle that the magnetic meridian and geographical meridian, they are subtending. That is alpha. This is alpha. This we call as angle of declination. Now, if this is our magnetic field, what we can do, we can at least resolve the magnetic field. If this is the axis, this is the angle, the axis with which the angle is being made, we term it as cos theta. So this becomes B, what? Cos theta. Theta means your delta, and this becomes B sine, not theta, delta. B sine delta. Fine. So what is the horizontal? This is your horizontal magnetic field. This is the vertical magnetic field. Now see class, what is the horizontal magnetic field? Horizontal magnetic field is B cos delta. What is the vertical magnetic field? B sine delta. If we take the ratio of PV over BH, what do we obtain? B sine delta over B cos delta. B will get cancelled and sine by cos will be tan. So this becomes vertical by horizontal is equal to tan delta. This is one relation which you have to remember. And if you have to find out the net magnetic field, that is given by under root BH square plus BV square. Why? Because cos theta in parallelogram law is 90 degrees in between BH and BV. This is what you have to remember. One more thing, at the magnetic equator, when we talk about the magnetic equator, at the magnetic equator, this delta becomes 0 degree, right? Angle becomes 0 degree at the equator. You can relate it with the equator. This becomes parallel. So this is 0 degree. So BH will become B cos 0 degree. That will be B. But when we talk about the poles, magnetic poles, delta is 90 degree. That's why I was saying Phi, that angle cannot be 90 degrees because magnetic pole makes an angle of 90 degrees. That angle has to be less. So anyways, Faiza has mentioned that it is 23. So this BH, this becomes B cos 90 degree. So this is 0. So horizontal magnetic field is 0 at the poles, and horizontal magnetic field is total, is the greatest maximum at the equator. These things you should remember. Note down this portion. This is your earth magnetism core part. From here, note it down. See class, now the next unit is your fourth unit. This was one unit. This was the third unit. First unit was electrostatics, which comprised of 2 lessons. Then second unit had only 1 lesson, that was current electricity. Third unit had 2 lessons of magnetism. The third lesson was based upon magnetism. Now the application of magnetism with electrostatics, that is electromagnetism. This is your fourth unit where you have 2 lessons, electromagnetic induction. This is the 6th lesson from your NCERT, and chapter 7, that is alternating current. That is the chapter 7th from your NCERT. So we'll start with the electromagnetic induction. We'll try to complete magnetic flux today. Electromagnetic induction. See, in the third unit, that is magnetism, what did we see? Firstly, in unit 2, in chapter 3, that is current electricity, we had seen that current was present, and current carrying conductor produced magnetic field, as we had seen in Biot-Savart's law, right? Now, if we do the opposite, see, current plus conductor is giving magnetic field. This is all what we have seen, and we know that this is true. Current plus conductor will give magnetic field, yes? A current carrying conductor produces magnetic field, and it's proved. This we have through Biot-Savart's law also. We can calculate also now. If we have certain data
Ma'am,
present with us, we will be able to calculate the exact value of magnetic field as well.
ma'am,
With all the thumb rules which we have studied, we'll be able to find out the direction as well. But if magnetic field is present in a conductor, will it produce current or not? This was the question that arose, and yes, this was solved by Faraday. Answer to this is yes, that magnetic field also present in a conductor can produce current, means reverse of this can also be possible, is also possible. So this was given by Faraday. Faraday during his time gave a contribution in this section of physics, and under electromagnetism he performed certain experiments, certain rules he gave. Now see, among this first topic is magnetic flux. Magnetic flux is similar to electric flux. EMI is also a very short lesson. This will also not take a lot of classes. Magnetic flux basically means number of magnetic field lines which are crossing area normally. Means the way this is exact same definition as of electric field. Suppose these lines are making an angle of 90 degrees. So number of magnetic field lines crossing an area normally. What is the number of field lines? 1, 2, 3, 4. So the magnetic flux will be 4. But see, again, the same problem arises. That is, if the magnetic field lines are uncountable, and if you have a space where you are not able to count the exact number of field lines, so how will you get the answer? Every time you'll not be able to calculate the magnetic field lines by merely counting it. So what you have to do? You have to know a formula. You have to know a particular integration so that you can integrate it throughout, or you at least have to have a formula for the calculation of the magnetic flux. This is exactly similar to electric flux, but Gauss law in magnetism is different, which we have already discussed in our chapter 5. Now in chapter 6, we are just focusing on magnetic flux. So same way, suppose this is a surface. Surface area is S. S is the surface area. Fine. This is present in a magnetic field. It's present in a magnetic field. Let me draw it in this way. A little inclined, so you will be able to figure it out. This is a surface area. This is a surface having surface area as S. Let's say certain magnetic field lines are crossing it. This is the magnetic field line. We take the normal perpendicular to this. This is known as area vector, perpendicular to the plane. So the angle that is made between the magnetic field and this area vector, this we call as theta. This is not the angle with the plane. This is the angle between magnetic field and the area vector, which is theta. Everything we have discussed, all the terminologies. Again, I'm repeating, theta is the angle between the area vector and magnetic field. It's not the angle between the plane and the area vector. Fine. So what is the formula? Formula is exactly the same. That magnetic flux, this is B dot S, which you can say BS cos theta. That is magnitude of B surface area into cos theta. This is it. B is magnetic field, S is surface area. This is cos theta. It's a scalar quantity. We have one unit as Weber, or one unit is present. See, SI unit of magnetic field is Tesla and surface area is meter square. But more often we use Weber. So easy topic, magnetic field. It's not difficult. Questions, okay, noted down. Then we'll discuss the question. All those who have completed, please sign into your accounts, attempt the after class assessment. Next week, we'll discuss this. So we'll try to cover this lesson. Most probably in the next week, this will be completed. It's a very short lesson. Just revise magnetic flux income. Thank you so much, class.